Hi, Casey.
Hey, Mason, what's up?
Well, me and my friend Lee have been breeding snakes, and we were wondering what kind of statistical test we could run to determine if our observations constitute a satisfactory approximation of the expected ratio. And I heard you were in genetics and wondered if you could help.
I sure can. It sounds like you guys need to perform a chi-square test. It can tell you how far your observed results can deviate from the expected and still be attributed to chance.
Well, how do we perform this test then?
Well, luckily for you, I've been practicing. So I have a chart already all drawn up.
Looks pretty complicated.
Actually, it's really easy. First, you need to know the chi-squared formula, which is chi-squared equals the summation of the observed minus the expected squared all over the expected. First, you need to know the phenotypes that you observed. So what kind of phenotypes did you observe?
When we bred the snakes, we got 25 that were normal pattern and normal colored, like these guys. And then we got 12 that were albino with a normal pattern. And then 8 with normal color and a striped pattern. And then 3 that were albino and striped.
Okay, so now we need to work out what the expected results were. It sounds like you performed a dihybrid cross.
We did perform a dihybrid cross, and we had 48 offspring, if that helps.
Well, you know in a dihybrid cross, the expected ratio is 9 to 3 to 3 to 1.
Heard that.
Well then, so we need to divide 48 by 16 because 9 plus 3 plus 3 plus 1 is 16, and then we'll figure out the expected.
Oh. And then, like, 9 times 3 would be 27, but maybe we're getting ahead of myself. Or not. 9 times, what would be the next one? 3 times 3?
3 times 3.
Yeah, 9. And then, let's see, 3 times 1, that would be 3.
3. Awesome. So we get these as the expected values, and then we just complete the math. Of the observed minus the expected, that value squared, and then that value over the expected. So 25 minus 27 is negative 2. 12 minus 9
3.
is 3. 8 minus 9 is negative 1. And 3 minus 3 is 0. Then those values squared. Negative 2 squared is 4. 3 squared is 9. Negative 1 squared is 1. And 0 squared is still 0.
This next one seemed a little complicated, but I think I could figure it out if I think hard enough. Say 4 divided by 27 would be 0.15. 9 divided by 9 would be 1. 1 divided by 9 would be 0.11. And then 0 divided by 3 would be 0.
Alright, and then to find the chi-square valued, we just add up this final column to get a sum of
1.26. But what does that mean?
well, a perfect result is going to be 0. So the closer your value is to 0, the closer your observed results are to the expected. We use a standardized table to decide whether any deviations from the expected are due to chance alone. First, you need to find the degrees of freedom. The degrees of freedom is found by any possible phenotypes minus 1.
Brilliant! So we have 4 possible phenotypes, and that would mean that our degrees of freedom would be 3.
Right, and then you search for the row that it's approximately where your values fall. Once you find the closest value, you read up to the probability of your results being due to chance alone. It was arbitrarily agreed that any hypothesis less than 5% would automatically be rejected.
So our value is 1.26, so it would fall here. And would be between 50 and 80%, so we would accept our hypothesis.
Exactly, and that's all chi-squared is.
We did it!